We are facing society's greatest challenge yet, climate change. With the effects and potential damages well known, governments across the world have implemented laws, regulations and incentives to lower greenhouse gas emissions. Developed countries, such as the UK, provide the greatest share of emissions into the atmosphere and have affirmed their intentions to lower emissions further in the coming years. One of the largest sources of greenhouse gases in the UK is the residential sector, which constituted 19% of all UK emissions in 2019. The built environment contributes significantly to climate change, and one method to reduce the UK's output is the implementation of the Passivhaus standard across the residential sector. In 1996, the Passivhaus Institute was founded in Darmstadt, Germany, to address efficiency standards in properties in developed countries, with an aim to reduce the running carbon emissions. The Passivhaus standard was written at this time and provides a set of criteria for residential buildings. Upon meeting these conditions, the house can be defined as passive. Overall, a passive house meets these general requirements. It has an exceptionally low heating demand of less than 4 kWh per metre squared per year. It has an airtight envelope with less than 0.6 air changes per hour. It contains outstanding insulation with a lack of thermal bridges. The house's U values do not exceed the standards set by the Passivhaus Institute. The building uses passive solar gain to meet as much of its heating demand as possible, and the primary energy demand of the building is less than 120 kWh per metre squared per year. Gecko Architecture's passive house meets all the requirements set out in the Passivhaus standard, which results in a home with a minimal environmental impact owing to extremely low heating and primary energy demand. Throughout this presentation, we will describe and explain how this house meets the Passivhaus standards, detailing its key passive features. As well as designing a passive house, Gecko Architecture was commissioned to ensure that the building is sustainable, with as low an environmental impact as possible. A sustainable building is a house that can be used for its specified purpose for a long period of time without causing environmental damage. Measuring whether a building is sustainable is challenging, as many factors must be taken into account. For example, is the building built sustainably? Was proper care and attention taken during construction to limit damage to wildlife and not waste resources? Does the building consist of sustainable materials using substances that can be reused and recycled and not just thrown in landfill? Does the structure sustainably use, capture and store both water and energy while limiting waste? And how does the building affect the well-being of its occupants? We may not always pay attention to how our actions affect the climate and the environment around us, from driving short distances, unnecessarily turning on the heating, using too much water and not making a home which considers nature and encourages biodiversity. Having a house that is specifically designed to be sustainable will invariably help the occupants lower their own environmental impact. One method to measure the sustainability of a building is the use of the Building Research Establishment Environmental Assessment Method, or BREEAM for short. This measures a variety of factors to judge whether a building is sustainable or not. Using this method, the house achieves an outstanding rating, meeting 85% of requirements. This presentation shall not only look at how this house meets passive standards, but also look at what makes it sustainable and how it met the BREEAM criteria.
The building is situated on a lovely plot at the southern foot of Ekstrom Falmouth's Penryn campus. It is unshaded and surrounded by a large green space, which will help the occupants feel connected to nature in their sustainable house. There are many local amenities, including the campus, a library, primary school and college, all within walking distance. If further travel is required, the house is also close to a bus stop and train station, and is of course accessible by car.
Gecko Architecture started the design process by studying other buildings, specifically sustainably designed passive houses built on a similar topography to our site. This inspired us to integrate the home into the hill, reducing supporting material costs and helping integrate the house with the environment. The many cantilever designs of buildings in Rotterdam also influenced our design. Not only did the cantilever improve the aesthetics of the house, but by limiting ground contact, also reduced the impact of radon gas, which is prevalent in Cornish bedrock. The cantilever also served as a carport, satisfying the client's desire to have a sheltered space for vehicles, but did not require insulation and additional material costs that a garage might have. The cantilever also acts as brise-soleil for the first floor. The shape of each floor was influenced by Passivhaus criteria. It was imperative that the home have a surface area to volume ratio of 0.7. Cuboid shapes have a far better ratio than more complex shapes, and so this was implemented in the design, leading to a surface area to volume ratio of 0.67. The floor plan was designed around the client's specification and requirements, whilst still meeting building regulations and Passivhaus criteria. The client required a kitchen and breakfast room, utility room, plant room, lounge, dining room, study area, 4 bedrooms, appropriate bath and shower rooms, appropriate water closets, workshop and garage space for at least one vehicle. Our design places the plant room, utility room, water closet and workshop on the first level, with an additional entrance leading out to the 2 vehicle carport under the cantilever. The second floor contains the main entrance, leading into the lounge, dining room and then the kitchen, with a large bathroom centrally placed near the stairs. The third floor contains all the bedrooms and a dual access bathroom with a large shower. Each room has space for a desk, wardrobe and bed, with the master bedroom being 23 meters squared. There are windows in every room, facing either north or south, allowing for passive heating and cooling, whilst providing an exquisite view of the surrounding areas and acting as fire escapes. The doors in each entrance room are placed to prevent air pressure changes in the house.
Using a reinforced concrete pad covering the entire footprint of the building, we supported the 3-storey partial cantilever. With the aim to reduce the environmental footprint of the foundation, the concrete used for the pad is Hansen Eco Plus, saving 138 kilograms of carbon dioxide per cubic metre compared to regular concrete. In a normal build, the foundation is one of the biggest thermal bridges. To minimise this, the foundation design utilises interlocked foam boards manufactured out of recycled insulation to achieve a thermal conductivity value of 0.105 watts per metre squared Kelvin. The foundation also includes an integrated radon membrane as is required for all new builds in Cornwall.
The house was built around a timber framework composed of glulam beams supplied by Duchy Timber. Glulam beams are glued laminated timber which can replace steel as a sustainable alternative. The glulam beams were constructed from locally and responsibly sourced timber with a lower carbon footprint due to low travel miles. Timber is an ideal building material as it is not only sustainable but also lightweight and can be constructed into a frame without creating thermal bridges. The timber frame also acts as a thermal mass, helping to regulate the temperature of the house. Additionally, it acts as a store of carbon, helping to reduce climate change. It is no wonder that it is one of the most common building materials in the world.
According to the Passivhaus standard, U values of walls and roofs contained in the airtight envelope must be between 0.1 and 0.15 watts per metre squared Kelvin. To achieve this, the walls have a width of 360 mm and consist of 2 air and watertight membranes, between which the insulating materials lay. The main insulating material is warm cell, chosen as it is made from recycled materials and has reduced associated carbon emissions. In addition, it displays excellent thermal properties, providing superb heat retention and noise insulation, allowing the house to meet passive standards. On parts of the roof, there is a layer of green facade applied. This was done to promote biodiversity and compensate for the land used by the house, as well as acting as a store for carbon within the fabric of the building. In some designated areas of the house, there are larger service air spaces to allow for the MVHR pipework to fit in the walls.
The triple glazed Combina passive windows were sourced from Catspec and allow for maximum insulation without disproportionate costs being incurred from increasing the number of layers of glazing. As well as a U value of 0.75 watts per metre squared Kelvin, the windows provide excellent sound insulation from nearby activity or construction work. For the front and back doors, the Green Building Store provided triple glazed timber frame entrance doors with U values as low as 0.56 watts per metre squared Kelvin and a 98mm profile. FSC certified timber from redwood and oak make up the bulk of the door, with an FSC certified Akoya timber drip rail for durability. The bathrooms were stacked on top of each other to reduce the distance the water had to travel, minimising the time waiting for hot water as well as pipe and labour costs. 100% recyclable PVC piping was used for all of the plumbing. Wastewater heat recovery was performed by a mechanical ventilation heat recovery unit and a compact service unit. Responsibility for sewage treatment was taken away from the public sewage system and a domestic microbial sewage treatment plant was integrated into the house design. This caters to 6 adults and passively processes effluent until it is safe to release into natural terrain for drainage. This model was obtained from Tricell and is called the Novo UK6 and costs roughly £2,500. To reduce water demand, a rainwater harvesting system was purchased and constructed on the roof of the building. The rain was collected and stored in a 7,500 litre tank underground until the water could be supplied to the toilets, washing machine and outdoor taps. The model was purchased from Stormsaver and is the Monsoon Eco 10 system, costing around £5,500. This was a slightly larger tank than is normally used in domestic properties, but was chosen due to the heavy rainfall in Cornwall relative to other areas of the UK. To reduce the impact of household waste, the Good Ideas 140 litre twin chamber tumbling composter was installed to compost food and garden waste. Chambers could be rotated 2 to 3 times per day, allowing the detritus to mix and encouraging decomposition. This resulting compost could then be used on the fruit and vegetable patches. This decreases the carbon costs of maintaining a garden, as the compost does not have to be packaged or transported, and it also reduces the amount of waste going to landfill.
The heating demand of this building was only 4 kilowatt hours per metre square per year, resulting in an annual heating demand of 992 kilowatt hours. This is 8 times lower than the average heating demand in a property in Plymouth, and highlights how exceptional the heating technology in this house is. This low demand is due to the outstanding insulation, highly efficient MVHR system, and the large window area, which introduces a high solar gain. The south-facing windows allow sunlight in through the day, warming the interior, and the larger the windows, the greater the heating effect. This effective use of passive heating contributes significantly to the overall heating of the house. The rest of the heating demand is met with the use of an air source heat pump with underfloor heating. To save cost, only the first and third floor used an underfloor heating system. This was because heating demand is so low and the insulation of the house is so effective that only 2 floors of underfloor heating were deemed sufficient. The cost of the underfloor heating was £45,000, including insulation. While the heating demand is low, the cooling demand is exceptionally high. It is at its highest in the summer months, where the house's large window area and exceptional insulation trap heat inside, and the building risks becoming uncomfortable for its occupants. To cool the building down, the air source heat pump can be reversed to exhaust heat from inside the house. The issue is that this requires a lot of energy, which can't all be met by the solar panels. As a result, the house requires a very high energy demand in the summer. However, not all cooling solutions are mechanical. Passive cooling with the use of brise-soleil has also been implemented. This is external shading that casts the south-facing window into shadow when the sun is at its highest and hottest during the summer, lowering the passive heating effect. Brise-soleil can reduce the heating effect of the sun by a maximum of 80%. The passive heating is still effective in winter and in the cooler hours of the day, as the sun can heat the house when it's lower in the sky. The house may also be cooled by opening windows to further minimise the danger of overheating during the summer months. In order for the house to meet Passivhaus standards, it must have at most 0.6 air changes per hour. In a normal home, this is usually exceeded due to drafts and air flowing through cracks and fenestrations. However, in a passive house there is an airtight envelope to make sure it is as firmly efficient as possible. To then meet the Passivhaus standards for airflow, a ventilation system is used, keeping the house full of fresh air. This comes with additional benefits, such as the filters in the ventilation system, keeping out pollutants, toxins, pollen, and reducing the likelihood of mould, so the occupants can have an internal environment that not only feels fresh, but is also better for their health. MVHR stands for Mechanical Ventilation and Heat Recovery. This is a unit used to power the ventilation system and recover heat. The model in the house is a Zehnder ComfoAir Q450, the most effective system on the market, with a recapture efficiency of 96%. This contributes to the building's efficiency and low heating demand, as heat is recovered by the heat exchanger within the unit. The heat is recovered from the air and passes into the domestic hot water cylinder. Zehnder's products were used for the ventilation system within the house, which accumulates to a cost of £7,000. The ventilation system operates by injecting clean, fresh air into so-called warm rooms while removing stale air from the wet rooms. The warm rooms are the bedrooms, living rooms, dining room, which benefit from a continuous flow of fresh air. The cold rooms are the bathrooms, toilets, hallways, and the kitchen, where there are foul smells and the humidity is at its highest. This exhaust air passes through the heat exchanger in the MVHR unit, transferring its thermal energy to the incoming fresh air and the unwanted exhaust air is ejected from the building. The Zender unit has an exceptionally low sound level of 32 decibels, with sound attenuators used within the system to further dissipate noise. The system is required to run with a volumetric flow rate of 270 meters cubed per hour to ensure air is removed from each room effectively. Finally, ventilation meets Passivhaus standards as the total air change rate for the building is 0.42, much lower than the maximum of 0.6.
With the focus of the design centered around sustainability, it was deemed critical that some form of renewable energy generation should be installed on the house. Solar PV was chosen as with the location of the house there would be an ample amount of sunlight to effectively generate electricity. Despite there being up to 80 meters squared available, only 20 meters squared was required to meet the demands of the house. The inclusion of batteries was also necessary to store energy and limit the amount of generated electricity that would be exported to the grid, especially in the summer months. Simulations predicted that roughly 90% of the energy demand could be met using a combination of solar panels and lithium-ion batteries. These batteries were selected as they are the more mature technology, which have been shown to be highly efficient and cost-effective when implemented in previous projects. Due to the nature of solar PV systems, many of the components will need to be checked every few years. The inverter has an estimated lifetime of 10 years and the panel up to 20. This shows that the inverter will need to be replaced during the lifetime of the panels, and the whole system is likely to need replacing throughout the house's lifetime.
There were numerous considerations and designs implemented to ensure this house caused minimal ecological damage whilst providing stimuli for maximum ecological growth. First, an environmental impact assessment was to be performed to give an understanding of the local ecology, so the house could be designed and constructed accordingly to this specific site. This greatly reduces the ecological impact that is often caused by construction projects. Next came the implementation of ecology boosting features. These include ponds, which create a great environment for amphibious creatures such as frogs and newts, wildflower meadows, which attract pollinating insects, creating an environment for birds and mammals too, bird and bat houses, which attract these animals and encourage breeding, log piles, which provide shelter for insects and hibernating mammals, and vegetable patches, which facilitate the sustainable growth of fresh food. All these features not only help increase biodiversity, but they also add to the aesthetic of the house and ensure occupants are more connected to nature, which will have a positive impact on their mental well-being.
The house complies with, and in most areas exceeds, the requirements of UK building regulations. One of note was fire safety. Since the building is 3 stories tall on the south side, special considerations were made on how to safely evacuate the building in a room with only south-facing windows. Fortunately, the majority of the building will have possible escapes that result in less than a 2-story fall. However, in a few instances where this isn't possible, occupants can escape onto the second floor roof and walk around to the north side where the fall is significantly reduced to only 1 story.
To assess the design's viability as a low-energy building and if it meets the Passivhaus requirements, the simplified building energy model as set out in the National Calculation Methodology was used. The highlight of these results is the EPC, in which the design receives an A with a rating of 8. This is due to the integration of renewables and a low-energy air source heat pump, which significantly reduces the energy demand of the property. The slide above shows the other performance metrics that SBEM produces. The total energy use is satisfactory, however if energy efficient white goods were installed, the equipment section could be significantly reduced. The same can be said for the energy demand of hot water. The heating demand graph reflects our design and the meeting of Passivhaus standards. The cooling graph, however, is wildly inaccurate as a result of the limitations of SBEM and the ISBEM software used to perform the calculations. The methodology does not take into account any of the passive cooling techniques we have implemented, such as the brise-soleil. Using Spong's architecture and the builder's price book in combination with quotes from manufacturers and supplier results in a construction and furnishing cost of £446,500 or £1,800 per square metre. The materials required to build the walls, roof, internal floors and the glue lamp frame represent the most significant portion of the costs at £140,000 or 32% of the overall cost. Labour was priced at £15 per hour and in combination with machinery rental is responsible for the second highest cost at £130,000 or 29%. Other significant costs include the MVHR, heat pump, windows and external doors. It should be noted, the costing includes an estimate for furnishings, white goods and other finishes such as the reclaimed wood flooring on the first and second floors.
This house meets the criteria set out by the client and the vigorous standards we hold ourselves to at Gecko Architecture and Consultancy. It provides a comfortable and pleasant living space, whilst ensuring sustainability at every possible stage, and meeting the Passivhaus standards. This has only been made possible through careful considerations, design and planning at every stage of the project. We are proud of our design and hope that it can not only meet the requirements of this brief, but can help pave the way of the future as more houses strive to meet Passivhaus standards and be sustainable.